We're going to look at compound and double angle formulae. Some prior knowledge for this will be circular functions, which again we looked at in lecture one. Some of the key concepts we're going to cover here is a proof of a compound angle formula. In fact, we're not going to prove it in this video, but I'm going to send you to a link on a time I've proved it before, so you can have a look at that. But we are going to demonstrate a compound angle formula. We're going to prove the double angle formula, and then we're going to take a look at the specialist maths formula sheet after that. So let's jump into our demonstration of a compound angle formula. So these are the compound angle formulas, and essentially they're just a bunch of rules that hold true when you're compounding angles. So you're either adding them or subtracting them. So for example, cos of x plus y, cos of x minus y, sine of x plus y, sine of x minus y, tan of x plus y, tan of x minus y. We're compounding these angles with adding them or subtracting them. And then they just equal all these things on the right. And these can be proved in various ways. As I mentioned, I've proved this second one in another video. So I'll put that link below. But what I thought would be a good idea is just like in science, you might get a demonstration of some property about the physical world. In maths, I feel like we can have demonstrations of mathematical properties. So let's think about doing that. What we've got here on the unit circle is three angles. And let's just break it down step by step. This first angle we're going to call X. So the one in blue is our angle X. And we can obviously change this angle by moving that point around. Okay, in pink, we've got the angle Y. And in green, we've got the sum of those two angles. So if we were to take X and add Y, so blue and pink, and then added them together, we would get the green angle. As you can see, when we increase blue and pink, the green angle gets larger, right? So interestingly enough, that's sort of what we get. Now, as you would have learnt from previous knowledge of circular functions, this point here, its x coordinate is cosine of x, and its y coordinate is sine of x. And similarly up here, this coordinate here is cosine of y, and then this coordinate is sine of y. And so just as a demonstration that this property holds true, the property says that cos of x plus y equals cos of x multiplied by cos of y minus sine of x by sine of y. So what we have over here is just that property. And all right, cos of x at the moment is 0.78. Cos of y is 0.33 minus sine of x, which is 0.662, multiplied by sine of y, which is 0.95. And you'll notice at the moment that that gives us negative 0.33, which is the cosine value of x plus y. Remember, cosine value is the x coordinate. So I've just sort of shown it down here for the green part. And you'll notice then the property holds true as we change, say, the x value. This changes to 0.63 and 0.78, and then the cos of x plus y changes to negative 0.53. So we can see that this property holds true all the way around the unit circle. And my formatting gets a little bit wacky, but you get the idea, hopefully. So that's one of the interesting properties of, yeah, well, that is a demonstration of the compound angle formula. And obviously that's not a proof, that's sort of just demonstrating that it's true. But as I said, check out the link below to see a proof of that. Okay, and obviously we could demonstrate all these other ones with similar logic. But what we want to do now is look at the double angle formula. So there are three double angle formulae. And as you know in maths by this stage, you can just rearrange things as much as you like. But if we just look over here first, we can say that cos of 2x equals cos squared x minus sine squared x. So that's our first double angle formula. And we think, let's just think about the terminology here. Double angle formula. Well, we've got cos of 2x. So it's the double of some angle x. Okay. Similarly, tan of 2x is 2 tan x divided by 1 minus tan squared x. And sine of 2x is 2 sine x cos x. Okay, we will actually prove this first one. So let's look at this first one here and see if we can prove it. what we can do is we can actually use the knowledge from the previous section, which was our compound angle formula. So if we want to prove that this is true, well, we can use cos of x plus y equals cos of x multiplied by cos of y minus sine of x multiplied by sine of y. But we know if we've got the double angle formula, if it's a double angle, then y is just equal to x. So we just get cos of x plus x. Okay, and then similarly substituting it in, it must be equal to cos x multiplied by cos x minus sine x multiplied by sine x. So therefore, cos of 2x equals cos squared x minus sine squared x. So I think that's a pretty interesting result. And then we can actually obtain two other expressions that can be useful for solving problems from this result. So what we can say is, all right, we can say cos squared x minus sine squared x. Okay, we can basically we can change this sine squared x using the Pythagorean identity. Now remember, the Pythagorean identity says that cos squared x plus sine squared x equals 1. So if we rearrange that a little bit, we can get that sine squared x is equal to 1 minus cos squared x. So sine squared x gets replaced with 1 minus cos squared x, and then you've got two groups of cos squared x. Cos squared x minus negative cos squared x is two groups of cos squared x minus 1. So this is another interesting result that pops out of the double angle formula. And, just to again state it, cos squared x minus sine squared x equals 2 cos squared x minus 1. Okay, and another thing we could also say is just doing the same thing, rearranging the Pythagorean identity in another way. We can replace the cos squared x part with 1 minus sine squared x. So we get that cos squared x minus sine squared x equals 1 minus 2 sine squared x. So they are the double angle formulae. And as you can see, we can sort of derive them from the compound angle formulas. Okay, let's have a look at what's actually shown on the Specialist Maths formula sheet. And if you come down to the second page of it, you come to this circular functions part, and you can see some of those identities that we sort of just showed. Here's our compound angle formulae. That's those 6 there. And then here is our double angle formula. There's the other double angle formula we just spoke about, and there's the double angle formula for tan. So you will get given these. You do not need to remember them. But hypothetically, you should be able to derive them. So you should hopefully understand where they come from. The other thing I'll just point out is Pythagorean identity, sort of the foundation for a lot of this is just there. Cos squared x plus sine squared x equals 1. Okay, hopefully you found that useful. If you did, please consider liking and subscribing and letting me know what you found helpful, and if there's any other ways I can help. Hopefully it's helping somewhat in your studies. So good luck, and I'll see you soon.